In this exercise, we will simulate heated flow in a pipe using computational fluid dynamics. The physical configuration that we will analyze and study is taken from an experiment that mechanical engineering students do at Cornell University in a lab course that they take. I love this particular exercise for two reasons. One is that there is an experiment corresponding to the simulation, so one can compare the simulation results to the experiment. Second, as a non-heat transfer person and somebody who is not trained in heat transfer, I have learned a lot about heat transfer fundamentals from doing this particular simulation. I hope this will be an interesting and enjoyable exercise for you. And I'll start by giving you an overview of computational fluid dynamics because some of you might not have come across it before. And at the end of this video, I'll indicate, how you could go to my free online simulations course and learn more about the ideas that I discuss over here. Okay, let me start by giving you an overview of computational fluid dynamics, or CFD. We now have CFD software that can simulate flow behavior by solving the governing equations of fluid flow numerically. And we will see what this numerical solution entails a little later. And this is thanks to the rise of computers. Our experimental setup, looks like this schematically. So you have flow in a pipe and you have three sections to the pipe. You have a unheated section in the beginning, which is a flow development section. So the flow just develops hydrodynamically over there. The second section, you have heat addition at the walls, and we'll see that later. And then the third section is insulated and the flow mixes adiabatically. And we'll do a CFD simulation corresponding to that experiment. And here is one of the results we will get, temperature distribution. And so this particular result is looking at temperature distribution in this particular region of the pipe. Okay, and blue is cold, green is hot, and red and yellow are hottest. We'll take a look at the results, in more detail once we get those. But that gives you an idea of the kinds of results you can get. One thing to keep in mind is that the CFD solution is approximate. Even with powerful computers and powerful software, you can solve these governing equations only approximately. And the CFD software we will use is Ansys Fluent, which is one of the main software packages used by professionals in industry, though the ideas that I discuss over here apply to any comparable CFD software. The benefits of doing the CFD simulation are that we can visualize the flow and do what-if studies. And by visualizing the flow, one can, gain physical intuition like I was indicating over here with this particular temperature distribution. And you cannot get this kind of view by just, from doing a few point measurements. So the visualization, makes apparent what the flow is doing in a way that you cannot see in the physical experiment. And in what-if studies, you can change like the flow parameters, you can change the geometry and so on and see how the flow behavior changes. And as you can imagine, this is much harder to do physically, but it's relatively easy to do on the computer. But there are also challenges associated with using CFD, and a big challenge is that if you put garbage in, you'll get garbage out. And CFD software is very good at putting garbage out. So you really have to know what you're doing. And you need to determine carefully how good the results are. Okay? So how do we do that? I'll show you how to do that by undertaking a process called verification validation, and engineers often refer to it as V&V. And you can think of, verification validation as a systematic process for checking results. Each of these terms, verification and validation, has a specific meaning, and I'll talk more about that soon. But to really understand how to verify and validate results and what is the difference between verification and validation, you really need to know what's inside the CFD black box, right? So the tool is a black box, and we'll give it user inputs, geometry, mesh, boundary conditions, and so on. And we'll turn the crank and we'll get color pictures and other results. And so we need to know conceptually how the black box is turning these user inputs into these color pictures and, drag coefficients or and so on. And so I'll talk more about that in my succeeding videos. And I will talk about the big ideas here, or the biggest of big ideas. And if you want to learn more, you can go to my free online course. So if you go to a browser and go to edx.org and search for Ansys, okay, and you will see my free course, A Hands-On Introduction to Engineering Simulations, and you can enroll. You need to register using an email account. It's all free. And when you come into the course, you will see Module 1 is Finite Element Analysis, Module 2 and Module 3 too. And then in Module 4, I get into Computational Fluid Dynamics. And, I teach Finite Element Analysis and CFD as variations on the same kind of ideas. So go through Module 4 and the big ideas in fluid dynamics, the big ideas in computational fluid dynamics. And laminar pipe flow is very similar to what we're doing here, except that there's no heating, and I do it very carefully. So if you want to learn more, that's the place to go to. Next, I will talk about the major elements of what's inside the CFD black box and what it tells us about how we can check our results through verification and validation.